So this is the question, shortest path in undirected graph having the unit distance. Okay, so this is the question given, like what to do this. We have given one undirected graph this, and we have given the source also along with it. And what we have to do, we have to simply represent the distance vector. And what it means, it simply give me that these are the corresponding the minimum distance from the source to this corresponding node I. Let's say if I'm talking about the node index number I, so this gives me it is the minimum possible path or minimum possible distance from this source to this corresponding node there. Okay, let's say if I'm taking this example there, see this is our the undirected graph there, and all are of taking as a one unit there, edges with respect to each other. Okay, so now what we have to represent, like what are the distances with corresponding to source node, and what's the given in the source node in the question. Let's say for this question there's a source node, let's say is given as a 0. Okay, it depends on the question. It doesn't our concept is remaining the same. It doesn't matter what is our source or our code changes according to it. Okay, so now what we can say, at every step we have to raise our nodes such that with the minimum distance should be applicable for it. Okay, so for the current node we have to go to its neighbor. Okay, and since all of the edge weights have the unit weight there, so every of the move cost the same there. Okay, means 1 there. Okay, so first time when we reached our node, so it's basically common sense, this is our shortest node when we first time reach our node there. Okay, so this is basically the BFS. Why BFS? Because we have to go here level by level there, and this is the work done by the BFS there. Means every of the level increases by 1, so that's why it gives me the intuition of the using of BFS. Okay, so in my future video you have to learn about the Dijkstra or further thing, but in this question I explain in the ending why I'm not taking the use of the Dijkstra there, or why I'm only using the Q there, why it is simply BFS, why not Dijkstra. Okay, so I'll explain it for the part there. Okay, so since here it is, since all are of unit edges there, so we simply use our BFS. So how to do this BFS, I have to write this because it might be the confusable at the later part here. Okay, so we have to simply use our BFS. For this, some of the typical intuition approach we have to use from for this question there. Firstly, I made the adjacency list. Okay, that is maybe the given in the question there, or we can either make according to our situation. We have to initialize our distance vector. Okay, so this is our dist vector. These are comprises of these nodes there, and these are all of the initialized with infinity. Don't confuse it. I have to explain you why I'm using this 0, 0 here. Okay, let's erase this part here, or let's just erase this. Okay, I think you might not be confused. Okay, so this is the same as all remain there. So what we do, simply we initialize our this distance vector. We have to use our the Q there. This is nothing but our Q. Okay, and what we do, simply we have to first initially push our source node to our Q there. Okay, so we have to push this source, and since what is the distance taken from the 0 to 0, it is nothing but the 0, because we are standing at that 0 already, so it means we have to update this as a 0. Okay, now apply the BFS. For each of the node, we firstly visit all its neighbors there. After it, we can say, if see this is my if I am reaching by this, so if distance of the node plus 1 is less than distance of neighbor, so we have to update. So what it means? It means this is nothing but the this is, let's say this is my current distance there. Okay, if I am reaching to the node, if it is, and it also taken the plus 1 there. Okay, means let's say if I'm reaching to this 3, so it already taken some kind of the distance, let's say D, and to reaching there it takes the distance 1 there. Okay, so that's why I'm using this. Okay, if it is comparatively smaller than our previous case, so when I'm approaching to the, let's say if I'm approaching to this 3 by this path, let's say in this question there is another path there. Okay, so if I am going to any of the path there, and if I'm reaching to this node and my current distance plus 1, if it is comparatively better, and in what case the better meaning is, it is if it is of the less length, there's what are the distance in our previous case. See, if this is the case, we have to simply update, and since we have to update this and then push this in our queue there. Okay, I don't do the dry run for the complete part there, because it might be understable there. So like we can say here, see, first initially I have to push this 0. Okay, now let's say if I'm writing there, initially the what is the distance to reaching 0, so it is nothing but the 0. From it we have to explore its neighbor. So what are its neighbor there? So it is nothing but there is a 1 there and there is a 2 there. Okay, it takes a distance +1 to reaching from 0 to 1 there, and it takes again the distance +1 to reaching from 0 to 2 there. Okay, it is nothing but the +1. Let's not confuse it. Okay, so what is this distance become? So it is nothing but we can say, just wait a second. Okay, so this is nothing but the distance become the 1 there. Similarly, this is the case for there, it is distance become 1. Okay, now come like talking about this node 1, initially length is 1 infinite, now its length become the 1 there. Okay, so is it comparatively like you can see, like we can see here that this is comparatively better for this. It means you have to update this path here. Okay, so we can update this, means we can update this by the distance there. So what it means, now we can say that that minimum distance from the 0 till this case. Okay, now coming to the 2 node there, it remain the 1 there. Okay, it like similarly for 1, and like after updating this part, we have to like since I have to remove this part here when I'm talking about this. So after updating this, we have to update this in our queue there. Okay, now after when we are talking about this using, so we are talking about this, we have to simply pop this part and simply discuss this similarly for this manner. Okay, and similarly update this. Like let's say if I'm to explain this, so this is nothing but our node 1 there. Okay, so what is the distance we are using or we have to take to reach this? So it takes me the distance, let's say what is the distance, it take it as a 1 there. Okay, after it can go to its neighbor there. Okay, so what are its neighbor? It is nothing but the 0 there, and it is nothing but the 3 there. Okay, so what are the distance, and already it takes a +1 there and +1 there. Okay, so its distance is 1 there and then +1, so it becomes the 2 there. And now if we see, initially in my earlier cases it takes the 0 distance, but now it takes 2 cases, means it is not the comparatively good solution, means we have to avoid that part. It is nothing but we have to go from 0 to 1, now again come to the 0, so that takes 2 distance, but it is like worthless. Okay, so we have to simply skip that part. Coming to 3, it takes me initially 1 then +1 there, so it is nothing but the 2, d is equal to 2, so it is initially infinite. Now we can update that part. Okay, so we can update this part here by 2. So like we can see, from 0 to 1 it takes 1, from 0 to 2 it takes 1, from 0 to 3 it takes the 2. Like you can go by either by this or either by this. Okay, similarly we have to since we have to update this 3, so we have to first remove this, and after it we have to insert our 3 in this. Okay, now when I'm talking to 2, and similarly this process goes on there. Okay, so I'm not going to for the further dry run of this. So coming to the coding part there, firstly I make the adjacency list for this question there, since initially we have given the edges there. So since this is an undirected graph, so that's why I have to go for the bidirectional case there. After it we have to initialize our distance vector, update our source vector with the 0 because we are standing at that, so it means the 0 for this. Initialize our queue there, putting the source in our queue. Now till the queue becomes empty, first extract over the node from the front and then eliminate delete from that queue. Now go to its neighbor. If we can say, if the distance to that node +1 if it is less than our distance of neighbor. Okay, so if that is the case, we have to update our distance of neighbor, and after updating we have to simply put this in our queue. Okay, so I think this might to be okay, so this is the thing there. And after it we can say, if let's say if there is any other case, replace unreached nodes. Let's say after the completing all of the cases, if any of the remain the infinite, and like in what case if it is infinite, it means it is isolated from this, or it can be the multiple components cases. So only in that case we have to make is distance I is equal to -1, means we are not able to reach to that distance. So simply update this, and after it return to distance there. Okay, now see, this is the question for this. This is the there are the further variation in this. Since here I can say here we can say our edge weights are the unit for the, or we can say the same for all of this. Okay, now what if we can say if weights are not same? Okay, so what are the case? So in that case what are we are using there? Okay, so in that case we are using Dijkstra or not, so we have to see this in my previous video, in my further video. Okay.